How are you? I hope you are doing great. So, welcome to eDays online multi-education platform. So, today we are going to start continuation of the topic of the real numbers. Yesterday we learned about the real number basics, and also we discussed some new examples and about the concept of Euclid division lemma method. Yeah, so today we'll continue and we'll solve the exercise 1.1. So, before starting our session, let me introduce myself. I'm Uday Kiran. I'm your maths academic specialist. I'll introduce our features and tools we have. So you have chat option with you in the live class session. You can interact with me through chat with the live tutor. So there are expert tutors are there. So you can ask any doubts and clarify your subject, clarify your doubts, and you'll get subject to knowledge. Okay. So and after the class, so you have revision classes also there. So you'll get in class PDF and for your revision material and try to revise all the topics after the class. We'll get also recording sessions. Try to revise all the topics and also observe the recording session, recording videos and all those things. And you can improve your subject knowledge. Okay. So without wasting our time, so let's get start our session. Okay. Yeah, I hope everyone's seeing the screen. The screen is visible. Yeah. So yesterday, let's recall what we discussed in the yesterday class. One second, guys. Yeah. In real numbers, we discussed about the basics and what is the real numbers and all those things. Real numbers is a combination of both rational number and irrational number. Okay. Yeah. And also we discussed about Euclid division lemma method. Before starting our session, so what is Euclid division lemma? You just recall all the concept. In the Euclid division lemma, so for given any positive integers that is a and b, observe carefully. So there exist unique integers q and r. Q and r is nothing but quotient and remainder. So here we can express in the form of a is equal to bq plus r. Okay? A is equal to bq plus r. This condition is very important, guys. 0 less than or equal to r and less than b. Here r is nothing but remainder and q is nothing but quotient and b is nothing but divisor and a is nothing but dividend. These all these things we learned in the previous session. Okay, I hope everyone recall all the concept. Yeah, and also we discussed about Euclid division algorithm. That is a technique to compute the HCF highest common factor. Let's see the step-by-step solution. Yeah, these things already we covered. How to find the HCF of the two numbers. So here this condition is important for any two positive. A is equal to B into Q plus R. Okay. Yeah. We completed all those things and we solved few examples about how to find HCF by using Euclid division lemma method. Try to recall here HCF of 4052 and 12576. You can take the bigger number, do the division method, and multiply. You'll get the you just substitute the remainder here. Take in the divisor. The divisor is 4052 here. Take 405052 here is the dividend and remainder as a divisor here. And after solving, you'll get the remainder 272 here. Now, what is the new divisor? That is 420. You can take 420 here. Why we are doing all those things? Still, you will get the remainder 0. Here, they get remainder 272, 148, 124, 24, 4. You can do finite number of steps. After finite number of steps, you get remainder 0. After getting the remainder 0, you just stop it here and observe what is the divisor here. What is divisor here? Here 4 is the divisor. You can take it as HCF of these two numbers is 4. You can write like this. Okay. All these things we learned in the previous session. Yeah, and also we solved all this example 2 and 3, and we completed the Kaju Barfi sum, right? 420 Kaju Barfis and 130 Barfis. How can we arrange in a stake, right? So we can arrange in a stake of 10 by finding HCF. Okay, let's get start our exercise 1.1. In exercise 1.1, we completed the first sum, I think, right? So, and also let's start the third sum here. How to solve the third sum by using HCF? What are the steps involved? The third sum. So in the first one, yeah, here exercise 1.1. So we'll solve the first question. Third one. What is the question of third one? HCF. We need to find HCF of 867 and 255. What are the steps involved? How to find? Try to recall, guys. So first take the bigger number here. So step one, you can take bigger number 8. Okay, first we'll just write in the form of Euclid division lemma. We can write the Euclid division lemma here. What is Euclid division lemma? A is equal to BQ plus R. This is the format, right? Let's erase this. A is equal to BQ plus R. Okay. What is the condition here? The conditions are really important. What I'm saying, 0 less than or equal to Q. So 0 less than or equal to R. Yeah, R less than or equal to B. R less than B. This condition is important. Okay. Now let's get start our 867. We can write 867 here. Okay. Divided with 255. 255. We'll do it the step by step here. Okay. So 255 with 867. So what is the new number we'll get? 86. 255 two time. Twos are 255, right? 255 into 3. Let's do it with 3. 15, 15, 16, 6, 7. 765. Okay. That's why 765. So we just multiply with 3, 255 with 3. So we'll get 765. So do it here with 3. So you'll get 765. Now what is the remainder you'll get? The remainder you'll get here 865 minus 2, 0, 102 you'll get. After getting 102, now what is the divisor here? We couldn't get the remainder is 0. That's why we can prolong the process. You can take the 255 here. The divisor here. Okay. Now do the again the division process 102 into 2. So you'll get 204 into 2. You'll get 204. Now 51. Still we couldn't get the remainder is 0. So that's why you can take the divisor 102 here, 102 here. Okay. So 51 times 2. Let's do it here. 51 times 2. So you'll get 102. Now finally we got remainder 0. We just stop it here. Let's write in step by step solution. Here, yeah, 255 into 3. Into 3. What is the remainder we got? The remainder we got 102. 102. Now the new divisor is, new dividend is 255. 255. And we can substitute with, solve with the 102. 102 into 2. And what is the new remainder we got? The new remainder would be 51. Okay. Now take that new divisor, that is 102. Dividend is 102. 102 with 51. 51 into 2. So you'll get remainder 0. Remainder 0. Now what is the HCF here? HCF here is HCF of this two number 867 and 255 is 51. You can write like this. I hope everyone understood how to do the step by step solution. Is 51. First, after giving that, you can observe the Euclid division lemma method process. So here, in the place of B, 255 is there. In the place of A, 867 is there. And in the place of Q, 3 is there. In the place of R, 102 is there. Okay. You can do the actual division process at rough work. It's not mandatory in doing, for your reference, I'm doing all those things. Okay. So what we have to take divisor and remainder, all those things. So that's why I'm taking this process. So you can note all those things. And finally, you can observe after getting remainder is 0. So you can observe that HCF is 51. Okay. So that is the third sum. I hope everyone understood. Okay. Yeah, let's get start our next sum. Read the question here. Show that any point, any positive integers in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. How can you solve this? Observe carefully, guys. I'll show you the example here. There is example question is there. Yeah, here 6 cube plus 1. Yeah, here the third example, what we did in the previous session. So you can take A and B, what we are taking in Euclid division lemma method. Okay, let's take like this. Once again. Yeah, let's take like this. Uh, yeah, observe each and every step here. Mm, 1 second, guys, it is lagging. My pen type is lagging. I just connected again. 1 second. Okay, now it is working. Yeah, observe carefully. Here the question they given. So 6 cube plus 1. Second one, show that any positive odd integers is in the form of 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. Okay, first we'll write. Let's do the next question. The question number 2. Question number 2. Yeah, so let A be any positive integer. And here, what is the question they given? It is in the form of 6 cube plus 1. So here in the place of B here they given 6. B here they given 6. Okay, by applying Euclid division lemma. So by Euclid division lemma, or else Euclid algorithm, you can write Euclid algorithm also. By applying Euclid algorithm, what is Euclid algorithm we learned about? So we learned about A is equal to BQ plus R, where 0 then equal to R less than B. This is what we learned. All right. Yeah, observe carefully, guys. So here in the place of B, what we have to take? The question they given 6q plus 1, 6q plus 3. So 6q. I mean, in the place of B, 6 is there. It's clear, everyone. Plus R is nothing but R depend on the question. So B here is 6. So B here is, let's compare with the condition here. B here is 6. So in between R, in between 0 and 6. So R we can take in between 0 and 6. So then R is the possible value of R. Let's write it here. Yeah, the possible value of R. What is the possible value of R? In between 0 and 6. In between 0 and 6. That's why we can take only. So 0, 1, 2, 3, 4, 5. Why? Because less than 6 we have to take. So that's why I'm taking 0, 1, 2, 3 till 6. Okay. Yeah. Now we'll do try with each and everything. So when R is equal to, let's take R is equal to 0, substitute over there, substitute in Euclid division lemma, what we'll get? A is equal to, so B here is also already 6 we are taken in the basics. So 6 into Q plus 0. So what we'll get? A is equal to 6Q. So A is equal to 6Q. Observe carefully, guys. If you take some random value of Q in rougher, do one thing. If you take random value of Q, if you substitute Q is equal to 1, what we'll get? 6 into 1, that is 6. If you substitute Q is equal to 2, 6 into 2, that is 12. If you take Q is equal to 3, you can take any value. So you are getting 6, 12, 18, 24. I mean, the multiple of 6. So all are even numbers. That's why we can write all are even integers we are getting. I hope everyone understood. Yeah. Now we can try with R is equal to when R is equal to 2. Sorry, R is equal to 1. Try with R is equal to 1. Now try with R is equal to 1. A is equal to. So B here is 6. And in the place of Q, 6Q. Now R is equal to 1. Okay. Now we'll get 6Q plus 1. Okay. Substitute any value of Q. If you take Q is equal to 1, 6 into 1. Let's try with 6 into 1. 6 plus 1, you'll get 7. If you try with 6 is equal to Q is equal to 2. 6 into 2, that is 12. 12 plus 1, you'll get 13. Now observe carefully, in this pattern, we are getting odd numbers. That's why you can write odd. We are getting odd numbers. So this is the rougher part. Try to erase all those things. I hope understood where we started. what is the question? I'll explain the question once again. So that any positive odd integers in the form of odd integers, we need to prove this 6q plus 1, 6q plus 3, 6q plus 5 are odd integers. I mean some integers. Okay. So that's why I just taken the Euclid division lemma algorithm and conditions. Here b is equal to 6. Why? Because 6q plus 1 in the place of b, 6 is there. In the place of b, 6 is there. That's why I'm taking b is equal to 6. I just substitute here. In between 0 and 6, we can take r values. We can take r values. Okay. We can take r values. That's why r is equal to we can take 0, 1, 2, 3, 4, 5. I'm doing some random guess. I mean, trial and error method. If you take r is equal to 0, you'll get 6q. If you take r is equal to 1, you can take 6q plus 1. Let's try with other numbers. Now, r is equal to 2. We already substitute r is equal to 0 and 1. Now, you'll get a is equal to 6 into q plus 2. R is equal to 2, right? Yeah. Now, 6q plus 2. Let's take that. If you take 6 into 1, that is 6. 6 plus 2, you'll get 8. In the place of q, you can substitute 2. The same method, guys. You can take q is equal to 2. 6 into 2, that is 12. 12 plus 2, that is 14. So you're getting even numbers. You are getting even numbers while taking q values. While taking q value 1, 2, 3, so on. Okay, you will getting even numbers. Now you can try with the r is equal to 3. Till where we have to do the trial and error method till 5. Because r is equal to 0, 1, 2, 3, 4, 5. R is equal to 5, you'll get 6q plus 5. Okay. So if you substitute carefully, so 6q, 6 into 1, 6 plus 5, it is 11. 12 plus 5, it is 17, like this. So again, you are getting odd numbers while you are taking q is equal to 1, 2, 3, so on. I hope everyone got some idea. Now try with r is equal to 4. A is equal to 6q plus 4. Okay. Now 6 plus 4, that is 10. So that's why we are getting even again. That's why I'm writing directly, guys. I think you understood each and every step. We are doing trial and error method. That's it. Now a is equal to 6q plus 5. Okay. Substitute any value of q. Any value of q is, it's up to you. You can do in rougher part. So substitute any value of q, you'll get odd numbers. That's why. So finally, they asked for that. What they asked for that? So show that any positive odd integers, which is in the form of 6q plus 1. So here, yeah, the first one, if r is equal to 0, we get even. If r is equal to 1, while we are substituting r is equal to odd numbers, r is equal to 1, 3, 5, like this. So we are getting odd numbers. So here r is equal to 3, r is equal to 5. So we are getting odd. So we can conclude that. What is the question? So for any, let's write here. Yeah, any positive odd is, any positive odd is, I mean, we are getting odd numbers, right? Odd is in the form of, what we get? 6q plus 1 and 6q plus 3 and 6q plus 5. Okay, you can prove like this. I hope you guys are understood, right? So where we started, the question they given, we have to prove that odd integers, I mean positive odd integers, where q is some integers. Then they said q is equal to some integers. That's why q is equal to some integer. That's why we started from here. Okay, so taking b is equal to 6 is important, guys. You just identify that. And condition, this step is really important. This step. Okay, a less than or equal to r less than 6 less than b. Okay, let's solve the another question. I hope everyone understood. Yeah, the next question would be in an army contingent, so of 16 members of march behind any army band of 32 members in the parade. The two groups are marched in the same number of columns. What is the maximum amount? If they ask for maximum column in each row, so we can do HCF. Okay, let's solve the, what is the next question? The third question. Let's solve the third question. So how to solve the third question? So here we just write, they given an army content 16 members is to march behind an army band. So that's why number of army Let's write it here. Number of, for your reference, number of army contingent members. Contingent members is equal to 616 or 618? 616. Let's take 616. And the number of army band. Army band is different and army content is different. Army band members. So members, you just write the given in the basic guides. So they given 32. They given 32. Now we need to find the HCF. Why? Because they asked for maximum number. Here they asked for maximum number. Maximum number is nothing but HCF. You need to find HCF of 616, 32. I think everyone knows the process. How to find HCF. First step is you just write the Euclid division lemma. So from Euclid division lemma, so you just write A is equal to BQ plus R, where 0 less than R less than B. You just write the condition. Okay. Now, what is the bigger number here? 616. So you can take 616. 32. You can do the division process at here. Yeah, 32 with 616. 616. 32 into 20. So you'll get 640. 640, it is greater than for 616. That's why you can take 32 into 19. So let's erase this. Let's erase this. Yeah, 32 into 19 will get 608. Let's write it here. 608. After subtracting, what we will get? So 608 minus we will get 8 is the remainder. 8 is the remainder. Now the next step, I think everyone knows. So we couldn't get the remainder is 0. You can take 32 here. 32 as a dividend here. Now 8 fours are 32. So you'll get remainder 0. Finally, you'll get remainder 0. You just stop it over there. So 32 into 19, the remainder is we get 8. Now observe 32 and 18. You can take here. So 32 here and 8 times 4 will get 0. So HCF of 616, you can confirm HCF of 616 and 32. So we can take the divisor, that is 8. That is 8. Now maximum number of, you can write like maximum number, they ask for maximum number of columns in each march. So you can write like maximum number of each column would be 8 members. Okay? In a parade, you can write like this. I hope everyone understood. Yeah, I'll give you a few seconds, try to observe. If you have any doubts, observe carefully if we do anywhere wrong. This condition is important. Let's erase this one. This condition is really important, guys. So based on the condition, we are doing all those things. Okay. Shall we move on to the next question? Yeah, let's move on. The fourth question. In Euclid division lemma, to show that square of any positive integers is either in the form of 3m plus 1 for some integers. Okay. The same question what we did in the second question. Observe they ask for odd integers 6q plus 1, 6q plus 3, 6q plus 5 like that. The same procedure. You can apply this Euclid division lemma here. Let's do it here. The fourth question. Okay, first read the question carefully. Square of any positive integer. This statement is very, very important. Square of positive integers. Okay. Before that, you just identify what is B here. In the previous question, we identified in the 6q plus 1, all those things, we identified what is B. Now you can identify what is B here. Identify B here. It is in the form of 3m and 3m plus 1 like this, right? Observe the hint here. X is any positive integer, you can write in the form of 3q plus 1, 3q plus 2 like this. Okay. So we can apply the same hint. Now you can write let A, B, any positive integers. In the question, they given also in hint. Positive integer and B we can take 3. Why? Because it is in the form of 3q plus 1, 3q plus 3 like this. That's why you can take B is equal to 3. Okay. I hope everyone understood. Now by you applying Euclid division lemma, the same process guys, nothing else. Euclid algorithm. What is Euclid algorithm? We found. Let's write it here. Yeah. So A is equal to BQ plus R. The conditions. What are the conditions we learned? So here 0 less than R less than B. Okay. Now already R we got 6. Sorry, B we got 6. I'm sorry. So B we got 3 in this question. Previous question it is 6. I'm sorry. So B here is 3. In between, in between 0 and 3, we can take R. We can take R, right? So now possible values of R. Possible value of R. What are the possible value of R? Observe carefully. In between 0 and 3. In the number line, between 0 and 3, what are the numbers have? 0, 1, 2. Right? And then, so I hope everyone understood. Now let's do the trial and error method. When R is equal to 0, we'll try each and every R value. When R is equal to 0, substitute in the Euclid division lemma, that is A is equal to BQ plus R. Let's substitute here. So A is equal to B. B here is 3. Q, we can take Q. And R, just now we got 0. So finally, we'll get 3Q. But question here is, guys, observe carefully. Question here is, we can do square of any number. Square of any number is nothing but we can do squaring on both sides. We got finally A is equal to 3Q after solving this. Now you can do squaring on both sides. What you will get? A whole square, 3Q whole square. You can write like this. Yeah. Finally, we got A square is equal to 9Q square. 9Q square. So we can write like this A square, 9Q square. We can write 3 into 3Q square. 3 into 3Q square. So 3 into 3Q square, you can take a variable M. 3Q square, you can take variable M. Okay, why? They given hint here, you can take the variable after squaring on that, you can take variable M. So we got 3M. I hope everyone understood. Let's solve the next step. Let's take when R is equal to 2. When R is equal to 2, A is equal to B cube. That is 3Q plus R is equal to 1. We tried. No. So let's take R is equal to 1 here. R is equal to 1, 3Q plus 1. Now what is the next step? So you just do squaring on both sides. That is A square, 3Q plus 1 whole square. Okay. So A square is equal to, it look like A plus B whole square. I just write the formula here for your reference. I think everyone knows A plus B whole square, right? A square plus B square plus 2AB. All right, 2AB. So simplify further. So you get 3Q whole square plus 1 square plus 2AB. 2 into 3Q into 1. Okay. So A square is equal to 3Q square is nothing but 9Q square. 9Q. We need to prove that it is mandatory. That's why I'm solving all these things. 1 plus 2, 3 are 6Q. Okay. Now observe carefully. So in 9Q square, let's write it here, 9Q square plus 6Q. Can I rearrange like this? Now in this 2, what we have to take common? What we need to take common? So here if you take common as 3, take common as 3. 3 into 3Q square plus 2Q you will get. Now I hope plus 1 is there. Now you can take this complete bracket part, take it as M. Now you'll get 3M plus 1 already there. You can write 3M plus 1. Observe carefully what we need to prove. 3M plus 1. Okay. After getting that square part, take that 3Q square plus 2Q, all those things as M. Okay. Finally, we got this one. Yeah, 3Q plus 3M plus 1. 1 second, guys. Plus 1 squaring 9Q square plus 6Q plus 1. 3Q square plus 2. Okay, finally we got this one. So here what is the question they asked for? What is the question they asked for? Here Euclid division method, lemma method. You can do squaring on square of any positive integer. So that's why we are doing squaring on both sides. So we'll get 3m or 3m plus 1. So you can write like, after that you can write like, so we proved that r is equal to 1 and 2. Now our next part is 2. You can take r is equal to 2. R is equal to 2. R is equal to 2. Why? Because so R value, possible values are 0, 1, and 2. We tried with 0 and we tried with 1. Now our part is to try with 2. So now A is equal to 3q plus 3q plus 2 and squaring on both sides. So 3q plus 2 whole square. Okay. Now it look like A plus B whole square. Again, you can write A square is equal to 3q whole square plus 2 whole square plus 2ab. 2 into 3q into 2. 3q whole square is nothing but 9q square plus b square is nothing but 4. Here, 2 3s are 6, 6 2s are 12. 12q, I just rearrange like this, 9q square for my reference plus q plus 4. Okay. Now if you take 3 as common, observe carefully from these two, 4 we can write it like, I can rearrange it as 3 plus 1 for my reference. So from this 3, so if you take 3 as common, what you will get? 3q square plus 4q plus 1 and plus 1 at the outside. Now you can take this complete inner bracket would be m. So you'll get 3m plus 1. 3m plus 1. Now a square is equal to 3m plus 1. Okay. Yeah, the same we got in the previous one, 3q plus 1 and all those things. So 3q plus 3. Now okay, they asked that some integers m. Integers m is nothing but here 3q square plus 4q plus 1 is an integer. And in the next previous one, 3q square plus 2q is an integer, that is m. Here also 3q square is an integer. I just erase this one, just rewrite marks. This is m. In the place of bracket, you can take m integer. Give me a moment. 3m. So finally, we proved that 3m plus 1 and all those things. Okay. Yeah. So I'll explain again, guys. So listen carefully. First, for any positive integers, they given, we need to prove 3m plus 1 like this. So you can take b is equal to 3. Why? Because it is in the form of 3q plus 1. Okay. So now Euclid algorithm, a is equal to bq plus r. So you just write the formula. Here b is equal to 3. You can take the limit between 0 and 3. Between 0 and 3, 0, 1, 2, 1, 2 is there. The possible value of r would be 0, 1, 2. 0, 1, and 2. You can take trial and error method. R is equal to 0, substitute over there. You get a is equal to 3q. So in the question, they asked for square of any positive integer. So that's why we are doing squaring on both sides. A square is equal to 3q whole square, you'll get 9q square. So that is 3 into 3q square, that is 3m. So you can do trial and error method with r is equal to m, r is equal to 1, you'll get like this. And you can do trial and error method, r is equal to 2, you'll get like this. After taking the common, so you can take the whole bracket would be m, whole bracket as m. Okay. I hope you understand. Let's move on to the next question, the last question. Yeah, Euclid division method show that cube. Previous question we did square of any positive integers. Now this time would be cube. The same method, 9m plus 1. So let's do it here. So this is the last question, that is fifth question. We don't require any hint. Here 9m plus 1. So that's why. So the same process, a, b, any real numbers. Sorry, any positive integers. Positive integers. Already given in the question. That's why I'm writing all those things. And b, what we need to take b? B here we have to take. Here b we have to take 3. Why I'm taking like this? I'll tell you later. Now by Euclid division lemma, apply Euclid algorithm. Euclid's algorithm. If you apply it, So you'll get A is equal to B cube plus R. The conditions, write the condition here. What is the condition? Conditions here 0 less than R less than B. So here B we taken 3. So that's why you can take in between R in between 0 and 3. Now possible values of R, let's write it here. Possible value of R. R we can take in between 0 and 3. What are the numbers are there? 0, 1, 2. These things already we did in the previous one. Now you can try with R is equal to 0. So A is equal to 3 into Q plus 0. So you'll get A is equal to 3Q. The question here is, guys, listen carefully, we have to do cube. Previously we did squaring on both sides. Now you can do cube on both sides. Cube on both sides. Because they stated here cube. Both sides. Both sides. So we'll get A whole cube is equal to 3Q whole cube. Let's do it on the next slide. So A whole cube is nothing but 3Q whole cube. Okay. A cube is equal to 3Q whole cube is nothing but 3 cube is nothing but 27. 27 cube. A cube is equal to 27. If you take 3 as common, so you'll get, I'm sorry, if you take 9 as common, let's take 9 as common. Why? Because we have to represent in the form of 9m like this. That's why I'm taking 9m. So here 3q cube. Now the whole bracket, what was inside there. So you can take it as m. So that's why we'll get 9m. So the first thing, 9m we have to find. Similarly, you can try with R is equal to 1. Now R is equal to 1. Let's try it. A is equal to BQ. BQ is nothing but 3Q plus R is equal to 1. Cube on both sides. Cube on both sides. Okay. So you get A cube is equal to 3Q plus 1 whole cube. Okay. How many of you remembered about the cube formula? I think everyone knows A plus B whole square. But what is A plus B whole cube? A plus B whole cube. I just write the formula for your reference. A cube plus B cube plus 3A square B plus 3AB square plus 3AB square. Okay. Let's solve it like this. A cube is equal to 3Q whole cube plus 1 cube plus 3A square B. That is nothing but 3 into 3Q whole square into 1 plus 3AB square. A here is 3Q and B whole square is nothing but 1 square. So I just substitute as usual, guys. Okay. Observe carefully. Here 3Q whole cube is nothing but 3 cube is nothing but 27. Q cube is nothing but Q cube. 1 cube is nothing but any power 1 power anything is 1. Okay. Here 3 square is nothing but 9. 9 3s are 27 Q square plus 3 into 3 9 9Q. I hope everyone understood. Now in this I just rearrange like this 27Q cube plus 27Q square plus 9 cube. I can rearrange like this. Why? Because if you take common from these two, these all those things, what we have to take common? Let's take 9 as common. So you'll get 3Q plus 3Q square plus 3Q plus 1. Okay. The same process what we are applying. So you can take the whole bracket would be M. The whole bracket would be M. So you can take 9M is plus 1. So you'll get 9M plus 1. So that is what we need to prove. The next one, 9M plus 1. 9M plus 1. While taking R is equal to 1, so you'll get 9M plus 1. I hope everyone understood. Now our job is to take R is equal to 2. The remainder R is equal to 2. Let's try with R is equal to A is equal to BQ plus R. Okay, so B is nothing but 3Q plus R here is 2. Now cube on both sides, so you'll get A cube 3Q plus 2 whole cube. Same way, the formula I just already write it in the previous slide. A plus B whole cube is equal to A cube plus B cube plus 3A square B plus 3AB square. 3AB square. Yeah, let's substitute here. A cube is equal to 3Q whole cube. That's why I'm writing each and every step, guys. Try to understand. So 3 into AB. a square b, that is 3q whole square into b, that is 2, plus 3ab square. 3a is nothing but 3q, b square is nothing but 2 square. 3q whole cube is nothing but, so you will get 27q cube. 2 cube is nothing but 8, and 3 into 3 square is nothing but 9. 9 threes are, 9 threes are 27, 27 twos are, so 27 twos are, you'll get 54. Okay, let's write in terms of 9. Okay, so 9, the 3 twos are 6. 6 into 9, 9 cubes. So why? Because in the next step we are taking 9 as common, right? That's why I'm keeping like this without multiplying. 3 threes are 9, and 4 into 9 cube. I'm taking in terms of 9, guys. After rearranging for my convenience, so 6 into 9 q square plus 4 into 9 q, and I just write 8 at last side. Okay. Now from all these things, you can take 9 as common. If you take 9 as common, so you'll get 3 cube plus 6q square plus 4q. That's why I keep 9 as there in the previous step, plus 8. Now what I said, the inner bracket completely you can take m. So 9 into the variable m, 9 into m plus 8 already there. So that is the thing we need to prove. The last one, 9m plus 8. 9m plus 8. Okay. Okay, I'll explain the from each and every step from starting. Okay, first, 1 second, guys. Yeah, first we need to, by using Euclid division lemma, we need to prove cube of. In the previous question they are given square. Now it is cube of positive integers. It is in the form of 9m, 9m plus m, 9m plus 8. Okay. Take b is equal to 3. Okay. So you apply the Euclid division lemma method. That is a is equal to bq plus r, and you just write the condition here. The condition is really important. Here b we taken as 3. That's why you just substituted 3 here. Okay. In between 0 and 3, what are the numbers we have? The possible value of r is 0, 1, 2, 3. The possible value of 0, 1, 2, 3. We just try with r is equal to 0. So substitute in the Euclid division lemma, a is equal to, in the place of b, 3 is there. In the place of q, q is there. In the place of plus, plus is there. In the place of r, 0 is there. Why? Because we are taking r is equal to 0. So a is equal to 3q we get. So here we are doing cube of any positive integer. Okay. So that's why I did cube on both sides. After doing cube on both sides, a cube is equal to 3 cube whole cube. So let's solve the next question. So a cube is equal to 3 cube is nothing but, for your reference, I'm doing rougher. So 3 cube into q cube. 3 cube is nothing but 3 into 3 into 3, that is 27 q cube. That's why I write right here. So we have to convert in the form of 9m plus 1. That's why I'm taking 9 as common. So only left is 3q whole cube in the bracket. So the complete bracket you can take m. So a cube is equal to 9m. So you can try with it, r is equal to 1. Now r is equal to 1. So you get a is equal to 3q plus 1. Cube on both sides. So you'll get like this. It look like a plus b whole cube. So substitute all the formula and convert in terms of what you are taking common. I just convert like this for my convenience. Okay, for my convenience. So I taken as bracket and 9 as taken as common. So I just taken as bracket and 1 at outside. Why? Because we have to convert in terms of 9m plus 1. 9m plus 1. The whole inner bracket we have to take m. Now the next thing would be, you can try with r is equal to 2. Use the same formula, a plus b whole cube. So you'll get the terms like this. After rearranging, I get the terms like this. The whole bracket you can take it as m. So 9m plus 8 is equal to, you'll get. Okay. Yeah. So I hope everyone understood the theorems part. The second question, fourth question, fifth question is look like similar. If you understand any one question, then obviously other two questions you are able to solve the other two questions. Okay. The third question would be it look like HCF, and first and third question are look like similar. So using HCF, you can find all those things. Okay. So we just started with the exercise 1.1 and we completed the exercise 1.1. And next concept would be fundamental theorem of arithmetic in the next class. Okay. I hope the session is informative. How to do Euclid division lemma method, where we started here. So we just started here with the real numbers. The real numbers, it is a combination of rational number, rational numbers, and irrational number. For irrational number, so here in the Euclid division lemma method, so this is the condition A is equal to BQ plus R. The condition would be A less than or equal to R less than B. Okay. So by using Euclid division lemma method, so we can find the HCF, highest common factor for any two indices. Okay. These things we already discussed. And how to find HCF between any two numbers, we can do the normal division method. Okay, apply Euclid division method. A is equal to BQ plus R. You just rearrange like this. Find the divisor. If you get remainder as 0, you just stop the procedure and observe the divisor here. Divisor here is 51. So you just write like this. 51 is the divisor. Okay. And other sums, questions 2, 4, 5 are look like similar. So try to revise all the topics what we learned till now and observe each and every step. So here the possible value of R is 0, 1, 2, 3, 4, 5. That's why I'm taking each and everything. R is equal to 0, R is equal to 1. I just tried with all the numbers. R is equal to 3, 4, 5, all these numbers. Okay. I hope the session is informative. So let's end up here. Let's meet on the next session with the fundamental theorem of arithmetic. Okay. Yeah, try to revise all the concept that if you still have any doubt, so just move backward and try to copy the what is the concept I explained. Okay. Yeah. So bye bye everyone. Have a good day.